Welcome to video 3 of my 6-part series on the basics of the AMC 10 math competition. My name is Michael Liu and I'm from Agora Math Circle. In this video, we will be going over combinatorics and probability. Specifically, we will start with going over the basics of combinatorics, then factorials, and then the permutation and combination formulas. After that, we'll be going over the stars and bars, probability, and finally, we'll go over a few example AMC 10 problems. Combinatorics are an area of math that focus on counting. And we'll be going over permutations and combinations first. Now, permutations are the number of ways to choose n elements from a set, with order mattering, which is very important because it's what sets it apart from combinations, which is the number of ways to choose n elements from a set without order mattering. And there will always be more permutations than combinations, assuming you're choosing the same number of elements from a set. So if we were given a set A, B, and C, and we were told to choose two of those elements without order mattering, we could choose AB, AC, and BC. However, with order mattering, we would have AB as well as BA, AC as well as CA, and BC as well as CB. So basically the difference is that you can also swap it around. And so that's why there's always going to be more permutations than combinations. So the first example that I gave, where there's only 3, that would be combinations, while the second example would be permutations. Having order mattering ended up doubling the number of ways you could choose 2 elements from the set. Factorials. So factorials will be represented by an exclamation mark. And you can see here that what it means is if you see n exclamation mark, that reads as n factorial. And that would be equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to times 2 times 1. So for example, if we had 3 factorial, that would be equal to 3 times 2 times 1, which is equal to 6. And similarly, if we had 4 factorial, that would be equal to 4 times 3 times 2 times 1, which would be equal to 24. So n factorial represents the number of ways a set with n elements can be ordered, assuming all elements are distinct. So for example, how many ways are there to order 4 people in a line? Well, the answer to that would be the number of ways to order n people will be n factorial. So there would be 4 factorial, which is equal to 4 times 3 times 2 times 1, which is equal to 24 ways to order 4 people in a line. Next, we'll be going over the permutation formula. The permutation formula is n factorial divided by, in parentheses, n minus r factorial, where n is the number of elements in the set, and r is the number of elements being chosen from the set. This is for use when order matters, which is what permutations are. So for example, find the number of ways you can choose 3 elements from a set of 7 elements with order mattering. The answer to that is you can just plug it into the formula and you get 7 factorial divided by 7 minus 3 factorial, which would be equal to 7 factorial divided by 4 factorial. And you can write it all out. And for that we would get 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. So we can cancel out the 4 times 3 times 2 times 1 from both sides. So we end up with 7 times 6 times 5, which is equal to 210 ways. Next, we have the combination formula, which is n factorial divided by r factorial times n minus r factorial. where n is the number of elements in the set, and r is the number of elements being chosen from the set. Now this is for use when order does not matter, which is what combinations are. So for example, using the same example as last time, the same numbers, except this time the order matters. So we still have choosing 3 elements from a set of 7 elements, and you find a number of ways you can do that, but order does not matter this time. So the answer for this is, we can just plug into the formula, same as before. You get 7 factorial divided by 3 factorial times 7 minus 3 factorial. And over there should be another 3 factorial. So you get 7 factorial divided by 3 factorial times 4 factorial. Over here we expand it, 7 times 6 times 5 times 4 times 3 times 2 times 1. And then that's the numerator. And on the denominator we have 3 factorial here, which is 3 times 2 times 1. And then we have 4 factorial here, which is 4 times 3 times 2 times 1. So after canceling the stuff from both sides, so we can cancel the 4, or we can just cancel this whole thing, we get 7 times 6 times 5 over 3 times 2, which is equal to 35 ways. So now I'll be going over an example problem. It is very, very important to know when to use the permutation formula versus the combination formula. So hopefully this example problem will help you to clear up any confusion as to when you choose which formula. So the problem is, Tony wants to buy 10 different colors of shirts, but he only has enough money to buy 6 shirts. How many ways are there for him to buy 6 shirts? So you see here that we're finding how many ways there are to choose 6 shirts from those 10 shirts. Well, now we have to ask ourselves, does order matter or not? Does the order in which Tony buys the shirts matter? So if you want to solve the problem for yourself, you can pause right now, and if not, I will reveal the solution right now. So the answer is that we use the combination formula because the order in which Tony buys the shirts does not matter. Ultimately, he walks away with the same shirts. It doesn't matter if he buys a blue shirt before a red shirt or the red shirt before the blue shirt. So because of this, we get 10 factorial divided by 6 factorial times 10 minus 6 factorial. And then there's a small shortcut that you can use. So basically we know that's 10 factorial divided by 6 factorial. We know that'll just simplify to the portion of 10 factorial before it starts to get to 6. So if we didn't simplify it, we could just write it out like this. 10 times 9 times 8 times 7 times 6, 5. So we write out the entire factorial. And then we have 6 factorial under it. Well, you can quickly see that everything after the 6 will just get canceled. So then we're just left with 10 times 9 times 8 times 7. And then we also have 4 factorial, which we then expand in the next equation. So we get 10 times 9 times 8 times 7 divided by 4 times 3 times 2. So then we can simplify, as you can see here, the 8 is canceled out by the 4 and the 2, and then 9 leaves on 3. So that's how we get 10 times 3 times 7. So finally we get 210 ways for Tony to buy 6 shirts. Another application of the combination formula is to find the number of ways to split X numbers of items into Y groups. So in this application, N is equal to X plus Y minus 1, and R is equal to Y minus 1. So remember, N would be the total number of elements, and R will be the number of elements you choose if you plug these values into the combination formula. So suppose we need to split 5 items into 2 groups. So in this case, plugging the numbers into the formula, so we get N equals 6, because the number of items is X, which is 5. So you can see here, and then this is X, and then the number of groups is Y, so 2 is Y. We plug it in to these equations. So we get n equals 6 and r equals 1. Using the combination formula, we get that there are 6 ways. So in case you're wondering for why this works, well, let's see how the combination formula represents this example. So there are 6 elements in the set. So we can just draw 6 blanks. Now we're finding the number of ways to choose each of those elements. So let's say we draw. So the reason why it's called the stars and bars is because you're representing the items as stars, and you're representing the divisions between the groups as bars. So you can see here that we have r equals 1. That represents the bar. Now, in case you're wondering why we have one less bar than groups, it's because for each bar, it creates an additional group, and you already have a group just starting out. So you see here that if we draw a single bar, we have 2 groups here, and then we have stars all the way over here. Additionally, you can have a group with 0. So you see here that we have a bar there, and then we just have all 5 items to the right of the bar. So seeing this is an explanation, a visual explanation of what's happening here. We're finding the number of ways we can place a bar into 6 slots. So the reason why n is equal to 6 is because it's the number of items plus the bar that you put in between the items to split them. So that's the total number of slots you have to put some kind of item or bar into. So if instead we have to divide it into 3 groups, well then, if we had 3 groups instead, then we'd have n equals 7, r equals 2. And then we'd have 7 slots. And we have to figure out, well, we could say put 2 bars here, and then we'd have 5 stars here. So now if we wanted this to be represented by the combination formula, we'd have 7 factorial divided by 2 factorial, 5 factorial. That would be equal to 7 times 6 over 2, which is equal to 21. So if instead we were splitting 5 items into 3 groups, we'd have 21 ways to do that. So now we have here an example problem involving the stars and bars. 12 pieces of candy must be distributed to 5 children. Each children must receive at least 1 piece. How many ways are there to distribute the candy? Now, note that the earlier mentioned method of using the stars and bars only works when each group can be any size, including 0. Well, in this case, the problem explicitly disallows groups of 0, since each children must receive at least 1 piece of candy. So we must find a way to modify the problem to allow us to use stars and bars. If you would like to try the problem for yourself, you can pause the video right now. Otherwise, I'll be going over the solution. So since each child must receive at least 1 piece of candy, we can automatically assign a candy to each child without affecting the end result, taking these candies out of the equation. So afterward, we must find a way to distribute the remaining 7 candies to 5 children, because we already gave 5 pieces of candy to each of the children, so 12 minus 5 is 7. Using the stars and bars, n equals 11 and r equals 4. The result is 11 factorial divided by 4 factorial times 11 minus 4 factorial, which is 11 times 10 times 9 times 8, divided by 4 times 3 times 2, which is equal to 11 times 10 times 3, which is equal to 330 ways. So in case you didn't get it the first time, basically, since each children must receive at least 1 piece of candy, we account for it at the beginning to guarantee it right off the bat. So if there were 5 children, we each give a single piece of candy, and after that, we don't need to worry about fulfilling that condition. And it doesn't affect the end result because we must guarantee it either way. So really, whenever you see a problem that has a minimum number of items per group, you could just distribute those minimum of items per group before using the stars and bars. If you still don't understand this, I'd heavily advise you to search online for more explanations and example problems involving the stars and bars, because it's quite an important formula that comes up. Now we will be going over probability. Probability is concerned with finding how likely a certain event is to happen. So a basic formula for finding probability is the number of possibilities for an event happening divided by the total number of possibilities. So for example, if someone was told to draw a straw from a jar with 6 red straws and 4 blue straws, and we're assuming that it's completely random and each straw has an equal chance of getting drawn, the probability of a blue straw being drawn will be 4 divided by 4 plus 6, which is equal to 4/10, which is equal to 2/5. Now that's only assuming that each straw has a random chance of being drawn and the person is closing their eyes. To find the probability, so in that case, the number of possibilities for the event happening, which in our case is drawing a blue straw, is 4 because there are 4 blue straws. And the total number of possibilities is 10 because there are 10 straws in total. And then we simplify that fraction to 2/5. To find the probability of 2 events both happening independent of each other, you can multiply the probabilities. So say for example, you want to find the probability of 2 blue straws being drawn, assuming that you replace the straws after they're drawn. So since the first drawing doesn't affect the second drawing because we replaced the straws, you can just multiply 2/5 times 2/5 and you get 4/25, which is the probability of 2 blue straws being drawn, assuming you replace the straws after you draw them. If you didn't replace the straws after you draw them, that would change the probability because the second drawing would be affected by the result of the first drawing. And something else I want to go over is how probabilities can be represented. A probability will always be between 0, then a probability, and 1. Now if you think about that, it makes sense because there's no chance for something, it doesn't make sense for there to be a negative chance for something to happen. And also it doesn't make sense for a chance for something to happen to be greater than 1, which is a guaranteed chance. I mean, how would something with 100% 10 chance to work? Probabilities can be represented as fractions, decimals, or percentages. So for example, we have here 2/5. You could also write that as 0.4, which works, and you could also write that as 40%. All of these are valid ways to represent the probability, and it depends on what form the question asks for. So now we'll be going over a few AMC 10 example problems. The first one we'll be going over is the AMC 10A 2018, problem 4. So this problem reads, how many ways can a student schedule 3 mathematics courses, algebra, geometry, and number theory, in a 6-period day if no 2 mathematics courses can be taken in consecutive periods? What courses the student takes during the other 3 periods is of no concern here. Pause the problem right now if you want to try to solve it for yourself, and remember is that if you find my explanation, if you don't like my explanation, you can always look for more on the Art of Problem Solving websites, and the link is at the bottom. So I'll be going over the answer now. So first we will figure out which periods are possible for the math courses to be distributed in, because there's a requirement that no two math courses can be taken in consecutive periods, which means they can't be next to each other. So the possibilities are 135, 136, 146, and 246. Those are easy to find just by looking at it, because you can see, well, if there are 6 slots and you need to have them separate from each other, well, you can obviously see, first of all, that's 135, so you can just label all of those. That's 135, 136, 246, and then 146. And then there's no other way to order the math courses so that there's no two math courses consecutive to each other. As you can see here that if you start at 1, well then the next course has to be either period 3 or period 4. If it's period 3, you can have 5 or 6. If it's period 4, it must be period 6. You can't have period 5 because then it locks out this 4 and 6, and 2 is also locked out. Or sorry, yeah. And then, well, you still have 3 in the end, so it's just the same thing as choosing period 3. If you didn't get that, it's fine, as long as you can just easily see by yourself that these are the ways, these are the possibilities in which you can order the math classes. Now that we have 4 possibilities for the periods in which the math courses could be taken, we need to figure out in which order they can be taken, because there are 3 distinct classes, and the order, in this case, the order in which they're taken does matter. So since there are 3 classes, the number of ways in which they can be ordered is 3 factorial. Just remember that factorials represent ordering, and that's equal to 6. So 6 orderings multiplied by 4 possible ways to put them into non-consecutive periods is equal to 24 ways in total to schedule the math classes. So that would be E. So just to recap, first we found the possible ways to order the math classes without them being in consecutive periods. And by order, I mean talking about like which periods to place the class in, not which class goes first, like algebra or geometry number theory. So first we ignore that and just assume they're all the same, and just look at the number of possibilities in which we can choose 3 periods where they're not next to each other. After that, we have 4 possibilities, and we have to multiply it by the number of ways we can change the order for each possibility. So after this, we do take into consideration that the 3 classes are distinct, and that there's algebra, geometry, and number theory. So the number of ways to order them is 3 factorial, which is equal to 6. So I'll be going over the 2017 AMC 10, problem 8. This problem reads, at a gathering of 30 people, there are 20 people who all know each other and 10 people who know no one. People who know each other hug, and people who do not know each other shake hands. How many handshakes occur within the group? If you'd like to try to solve this problem for yourself, pause the video now. If not, I'll be going over the answer right now. So there are 2 separate cases of handshakes we need to account for. Those between the 20 people who know each other and the 10 people who don't know anyone, and those between the 10 people who don't know anyone themselves. Because remember, handshakes only occur between people who know each other. So the 20 people will never shake hands with another person from the same 20 people group, while all 20 people from the 20 people group would shake hands from each person from the 10 people group, because the 10 people group doesn't know anyone. So and then the second case would be the 10 people group shaking hands among themselves, because they don't know each other either. So for the first case, each person from the 20 people group will shake hands with each person from the 10 people group, which would be 200 handshakes. Now for the second case, which is the 10 people group shaking hands within themselves, we need to figure out the total number of ways to pair 10 people with each other, because each handshake will be within a pair of 10 people. Now in this case, we use the combination formula because handshakes, it doesn't matter the order in which we pair people up. Because in handshakes, there's no first person to shake a hand, second person to shake a hand. It's both people simultaneously handshake. So we don't want a group of two people to be counted twice, which would have happened if we used the permutation formula. So that's why we use the combination formula. So to find the number of ways we can get two groups of two from 10 people, we get 10 choose 2, which would be 10 factorial divided by 8 factorial times 2, which is equal to 10 times 9 divided by 2, which is equal to 45. So in total, we would have 200 plus 45 handshakes, so 245 handshakes, which is B. In case you didn't get that explanation, you can always go back to this link right here, or you can just go into Google and search up 2017 AMC 10A Problem 8, and you can look at the solutions on the Art of Problem Solving website. So finally, I'll be going over problem 9 of the 2017 AMC 10B. This problem reads, a radio program has a quiz consisting of 3 multiple choice questions, each with 3 choices. A contestant wins if he or she gets 2 or more of the questions right. The contestant answers randomly to each question. What is the probability of winning? So if you would like to solve this problem yourself, pause the video right now and try it on your own. If not, I'll be going over the answer right now. So we can once again employ casework to solve this problem. In case you didn't know, casework is the division of a problem into specific cases that you solve individually to make the problem more easier to solve. And we did that with the last problem with the 2 cases. So to win, the contestant can either get 3 questions right or 2 questions right. So those are our 2 cases. Now the probability of the contestant guessing all 3 questions correct is 1/3 to the 3rd power, which is equal to 1 over 27. Now, the reason this is that the probability of getting 1 question correct is 1/3, because there are 3 choices for each question with 1 of them correct, and the contestant's choosing randomly. So there's a 1/3 chance that he happens to choose the right answer. And then there are 3 questions, so we can multiply them all by each other. So then we get 1 over 27. To find the probability of the contestant getting 2 questions right, we can pick one of the questions to be wrong. So the reason this works is because in order for him to get 2 questions right, and only 2 questions right, it means that he also gets one of the questions wrong. And it's simpler to figure out how to deal with one question rather than 2. So there are 3 ways to pick such a question to get wrong. So then we consider the probability that such a result will occur. Well, the probability that 2 questions are right and 1 question is wrong, assuming that it's in that specific order where the first 2 are right and the last one is wrong, is 1/3 times 1/3 times 2/3, which is equal to 2 over 27. And once again, we can multiply the probabilities because the events are independent of each other. However, since there are 3 possibilities for there to be 2 questions correct, we can multiply that probability by 3 because there are 3 ways for our conditions to be satisfied. And that probability, 2 over 27, only represents one of the possibilities, one of the orderings of the 2 questions and 1 incorrect question. So if you want to see that visualized, this probability we have here, 1/3 would be correct, correct, and wrong. Well, there are 3 ways to do it, because you can also have correct, wrong, correct, and you can also have wrong, correct, correct. So then 2/27 is just this one, but you also have 2/27 for that, and 2/27 for that. So in total, we have 6/27. So then we can add the 2 probabilities together, and which is this one and this one, leaving us with 7/27, which is equal to D. Now the reason why we can add those 2 together is, well, it's because it's that those are just 2 events that both satisfy our condition. We only need one of those events to happen, and those events are both mutually exclusive of each other. We can't simultaneously have all 3 questions correct and all 3 questions wrong. And because if we were requiring that both of these were to happen, saying that the contestant would take 2 tests, in 1 test he has to get all 3 questions correct, and in the other test he has to get 2 questions correct, well then we would have to multiply the probabilities together. But since this is the same test, and we could have either or of these probabilities, we add them, because we only need one of them, not both. So after we add the 2 probabilities together, we get 7/27. Now, if you haven't dealt with this before, it might be a little confusing. So the best way to improve is just to look at practice problems and read the solutions, and make sure you wholly understand them. So if you didn't understand my solution here, just go to the art of problem solving and look at the problem and try to get a better understanding of it. And as you feel that you get a better understanding for the slightly easier problems, you can start looking at the harder and harder problems. And eventually you'll be able to do them much more easily with more practice. So this concludes the 3rd video in my 6-part series. Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!